Hello class, this is to follow up what we did in lesson today, looking at their area under the curve. So let's recap what we established in class. That the area enclosed by a curve and the x-axis can be found by a definite integral. That's these guys with limits. Okay, that evaluating this kind of definite integral can actually give us a negative area value, not just positive. So what we need to do with those negative area values, we must subtract the definite integral that gives the negative area value when finding the total area. So in this example, we've just got a positive area only. But when it's below the x-axis, if we had another region of a graph, different function, and it fell below the x-axis, then an enclosed region there will in fact have a negative area. We must have a subtraction in front of the definite integral to accommodate, to compensate for that negative area, to make it a positive result. So let's apply that. Let's now think about this problem. What happens when the region is below the x-axis? Here. That's right, we have the negative area. We always must remember that. The definite integral will give a negative value. And we can see on the graph, this region is above the x-axis, so it'll be a positive area region. This area is below the x-axis, so it'll be a negative area region. Okay, and we have to remember to subtract the definite integral that evaluates this area from some starting point to some ending point. So let's go ahead and find the area using a definite integral. We've got a cos graph, and just by looking at the sketch, it looks like I've got two regions of roughly the same kind of shape. I've got one from the maximum of the cos down to the x-axis intercept, and then from the x-axis intercept down to a minimum. And kind of looks like the same shape, same size. So we can predict, if we're taking now the definite integral from 0 to pi on 2, 0 to pi on 2, which is this point according to the coordinate, then what do you think would be the total value we would get from evaluating such a definite integral? What do you think? Yeah? Oh, that's right. It will be 0. How come? Because the negative area is going to cancel out the positive area. Very good. So such a definite integral is not going to give us a total area. We have to split it up. So the correct expression we're going to have to use to get this area will be an expression that involves finding area 1, and then we have to, that's right, subtract area 2 because it is negative area. So let's work out, think about a definite integral for area 1. Has to be from the starting point, x value, and we can see that's 0, up to some upper limit, this coordinate. Now, what is that coordinate? This is our x-axis intercept of our cos of 2x graph. Okay, so that's something that must be found first. Let's go ahead and find that. Let's find when y is equal to 0. And we'll have put that into our rule. Cos of 2x is equal to 0. That means 2x is inverse cos of 0. Now, let's consider one value here that is closest to 0 when it gives us a result of the inverse cos of a value of 0. What angle will do that? Well, I know that cos of 0 degrees is 1 because I can see on my y-axis way up here. And then as I come down a whole quarter of a cycle, and a whole cycle is about 360 degrees around a unit circle, 2 pi. What's quarter of 2 pi? Yep, pi on 2. But hang on, this is the value for twice the value of x, 2 times x. So therefore x must be pi on 4. Very good. So there's our point there. It's pi on 4, 0. So I have now a lower limit for the first area, 0, and an upper limit for the first area is pi on 4. So, area 1. Let's put it all together as a total area expression. Area 1 is positive area, so I'm going to keep it as a positive definite integral from the lower limit of 0 up to the upper limit of pi on 4, that x-axis intercept of my function cos of 2x dx. Okay, now the next I have to subtract the definite integral that's going to give me area 2 because it's going to be a negative area. So the lower limit is the starting point of area 2, which is this point here. That is pi on 4. So my lower limit right down here, pi on 4, up to my upper limit, as we can see, pi on 2 is the x value for where the region finishes. Okay, so setting up our limits, now we put our function in, cos of 2x dx, and off we go. We want to integrate. Okay? Pause. Okay, let's see how we can use our CAS to assist us with evaluating this total area. We're going to set up our expression for total area. So come to the menu where we'll have our integral expression, so we can set up our definite integral with limits from 0 up to pi on 4 according to our expression there. So set that up, pi on 4 of our function cos 2x dx. Do the same for the second one, but as you can see, have to subtract that second definite integral. Now lower limit again from pi on 4, and it's like picking up where we left off. We left off at the upper limit of pi on 4, so in the next one we're going to start at that spot where we left off at pi on 4. Make sure we cover all the region with no gaps. Up to now an upper limit of pi on 2. Of our function. Alright, so we've put it in correctly. Let's evaluate it. We get a total area of 1. Interesting. Okay, now let's compare that to the sketch of our function. So I'm going to insert a graph. Let's sketch our function cos of 2 times x. There it is. Let's just look at a region of interest. changing the window so I can zoom in on my area that I'm looking at. There it is. Now, we were finding the area in between 0 and pi on 2. So, I'm going to come to Analyze Graph. And under Analyze Graph, I have 7, the integral. Now, this allows me to determine from the graph the area underneath it. So I click on 2 regions, there and at the end here. Now I just approximated where they are, but to get exactly on the right endpoints, I'm going to have to put a coordinate in at those points. So I click on the point, go coordinate and equations, 1 there, coordinate equations, 1 there, and now I can put in my values correctly. So I will have a 0, and this one was upper limit of pi on 2. So you can put it in as an exact value, and I get this. Now hang on, this is a very small number, almost like 0, but we got a total area not of 0, we got a total area of 1 looking at our definite integral. So finding the area underneath the curve using this estimation tool with the CAS again does not think ahead and doing a subtraction of this second definite integral here. They are almost cancelling each other out. So I have to be careful how I use this tool and split it up, like I have split up my total area into 2 definite integrals. So let's undo that. Now what I had to do is get that point of intercept, pi on 4, which is this point right here. So I'm going to grab a point, an intersection point between the x-axis and the graph, and find what is that coordinate. That is pi on 4. Now I'm going to do that again, Analyze Graph, to get my integral, and this time I'm going to do it from 0 up to 0.5, up to pi on 4, and I get an area of 0.5. So far so good. And then I have to do it a second time, Analyze Graph, integral, but now I'm going from pi on 4 up to pi on 2 of the function. So it's from that point up to that point. And we can see now that CAS is evaluating a negative area there, negative 1/2. So that's why it emphasised the importance of this subtracting the second definite integral. Because if I have 0.5 and I subtract the negative 0.5, I'm going to get a total area of 1, just like I had calculated.